Oh, good, good. Is that Kanye? What? I love your guys' creativity. I just looked for beach pictures and I figured that that was good enough, but no, this is excellent. Let me see if I can share my screen without my internet dying again. All right. Okay, are we in business? Okay, excellent. Let's see if we can make it through the end of the class here. Let me turn my own picture off because I can't handle this. Okay, there we go. All right, so we were talking about alpha, type 1 error rate. What is the rate of false positives that we are willing to accept? And there is a convention in the social sciences as to what that number should be. Would anyone like to tell me? Oh, fine. There's the chat window. Survey says 0.05. Yes. Everyone just decides that. There's nothing that says that you can't change it. So what 0.05 means is that 95% of the time you say no relationship there if not there. 5% of the time you say found it, but it was not there. Okay, that's the definition of type 1 error. Now, if you don't want to make a mistake, you are unwilling to have a high false positive rate, you change the alpha. You make it lower. So if I set my alpha instead to be 0.01, that means that 1% of the time I would have a false positive, and 99% of the time I would have a true negative. Okay, so those are the things we have to decide a priori, right? If we're willing to accept a relationship in either direction, two-tailed test, and how do we want to define what found it means? What's our error rate that we're willing to accept, type 1 error rate? Okay. Then there's a picture that I want to show you. Lecture. I think I lost one of my PowerPoints. It's the T. That's what I wanted to show you. Let me pull this up real quick. It should be in my history. There it is. Come on, you can do it. Nope. Here we go. Loading up the pictures takes a few seconds. That's all right. Help. No, I don't need help. He's not that kind. There we go. See, those of you last time who said that it was harder to stay, that it's easier for me to go too fast when you guys aren't in front of me to make me slow down. See, the universe heard you, and my computer is doing everything humanly possible to slow me down right now. Okay, I can see it in my side panel here. There we go. All right, this is the picture I wanted. We get to our friends Z and T. And then this one. Okay, this is our friend T. So the cut points that are on this picture, for instance, 1.96 or negative 1.96, that is your traditional cutoff for what is unexpected at an alpha of 0.05. So it's 2.5% on one side of the distribution, 2.5% on the other in terms of the area. What number that is exactly, where the cutoff is, that tells us where the 5% mark is, depends on our denominator degrees of freedom. That's a function of how many people we have and how many fixed effects we've estimated. So for instance, if I had 30 people in a sample, and to get my relationship, I needed to estimate a fixed intercept and a slope. then that's 30 people minus 2 fixed effects is 28 degrees of freedom, meaning points I haven't spent yet that I could. So if I go to my handy-dandy t-table, degrees of freedom 28 and an alpha of 0.05, my cut point would be 2.05. So that tells us where it is exactly that the 5% mark lies. So we decide to make a two-tailed test. We know what our sample size is, and we know what our alpha is. Okay. If you look at the numbers on this table, and I know they're very small, but the general tendency is that T has to be higher. The point to hit the magical 5% mark is higher. It's further out the fewer people you have. It's harder to hit the 5% if you have a smaller sample. Okay, back to my thing here. Okay. So these are the things we know ahead of time. Now we're in the game. We're trying to figure out what is our relationship. So for instance, if I have a slope, let me scroll up here. Try this. Hide this for right now. A slope conveys a relationship, right? The ingredients that go into a slope. There is the effect, and there are units of x and units of y. So if I tell you that my slope is 3, 3 is a meaningless number all by itself. 3 what? For every unit change in x, y goes up by 3. Is that a lot? Well, I don't know. Is y on a scale of 0 to 1,000,000? Then 3 is not very much. Is y on a scale from 0 to 10? Then 3 is a lot. So the slope conveys an effect in units of y and in units of x. So we have all three of these things here. Okay. What isn't part of the slope is sample size. It's irrelevant. There's nothing in the formula for a slope that's weighted or otherwise depends on sample size. Okay, that's not there. If we want to get an effect size, what we need to be able to do is keep the strength of an effect, but control for the units of y and the units of x. We got to get rid of them. So you've seen two examples of this so far. In computing a correlation, correlation is what we were focusing on predominantly, but there was a step right before it that's analogous to a slope. It's covariance. Yeah, this is going to take too long to pull up. I'll just do it off the top of my head. So we had one more thing here. Effect size. So in the context of linear models, we have our unstandardized slope. That's in units of y per units of x. Has nothing to do with sample size. Also we'd have no idea whether or not that's different than 0, whether that's in unexpected territory. If we want to correct that unstandardized slope for units of y and units of x, we want to get rid of units. I don't want a situation where I don't know what to do with the slope as a number, because 3 depends on what I'm talking about, right? That's not helpful. We can compute a standardized slope instead, which moves units of y and units of x, and then it puts it on a metric that we know what to do with. So a standardized slope ranges from -1 to 1, right? You know based on the direction which way the association is. So a positive standardized slope, say a 0.8, means that as x goes up, 0.8 tells us how many standard deviation units, standardized units. So if x goes up by 1 standard unit, y goes up by 0.8. That's what a standardized slope would mean. We all saw this in, not a type. It's not a type, it wanted to be that. Oh goodness, Excel, you're killing me. Okay. We saw this sort of thing as concept when did covariance, I don't here. Correlation. Covariance is what is computed directly as a measure of association between two variables. It is how far off the mean you are on x multiplied by how far off the mean you are on y as the root of that thing. And that's in units of y and units of x. So it's the same problem. If I told you you had a covariance of 16, you'd be like, is that a lot? I don't know, because it has units in it. So to be able to standardize that, and correlation is effect size that has an unit. So the slope, the unstandardized slope, or a covariance, those are measures of association that are unit specific. To be able to convey in a more absolute sense how strong an association is, how strong a prediction is, we need to remove the units and come up with a number that is readily interpretable because it's unit free. That is a standardized slope in general linear models. That is a Pearson correlation. It has that same quantity. Another effect size that you will see is Cohen's d. Cohen's d, you can also put this. I'm going to insert that here. Cohen, that's a person. Cohen's d, which is standardized mean differences. So that ranges from negative infinity to positive infinity, but it's in standard deviation units. So if I told you that I had a Cohen's d between 3-year-olds and 4-year-olds of 0.8, that would mean the 4-year-olds are 0.8 standard deviations different. So it's more common in comparing mean differences across groups to use Cohen's d and R. It accomplishes the same goal. It's a number that I know what to do with because I've corrected for the problem of arbitrary units. Okay, what we have anywhere on this little section right here is anything that tells us whether the size of the relationship is expected or unexpected, is significant. So what do we need to be able to do that? Well, we need to somehow get information about sample size into the story. So what we need is a test statistic, such as t, most commonly, or z, chi-square, or f. Those are other ones that will come up. The role of a test statistic is to adjust effect size for sample size. So in the formula to test a correlation for significance, that T formula, which I would pull up if my internet was not going to freak out on me. I don't have it memorized off the top of my head, further proof that you don't need to memorize formulas, but I know what goes in it. The correlation itself goes in it, and sample size goes in it. So now, the result of the T places us in the domain of that T distribution. Where are we in expected versus unexpected land? If we're talking about a test statistic for, here, let me put that there. I want one more line. If we're talking about tests in the context of a model. So Pearson's correlation is sort of a special case because you don't have to worry about the unstandardized aspect. Once you have a correlation, you've got your effect size. The effect size is directly given a test statistic. But in models, so if I want to talk about associations here, I'm missing one piece. And the piece that I'm missing is standard error. Standard error of a slope has three things in it. It has units of y, because the top of it is residual variance of y in the formula. It has units of x, because the denominator of it has the variance of x. And it has our reference sample size. So if we get our t-test statistic, that thing is your estimate minus your null hypothesis. So it's almost always the null, the thing that we're testing against is 0, but I'm putting that in there just for keeping that point in there, divided by your standard error. So if we look at what's unique now, units of x and units of y are going to cancel. What's left then, what the test statistic reflects, is the size of the effect and the sample size. So trying to put it all together then, your slope, your beta 1, that gives you the size of a relationship, but it's attached to units. If we want a unit-free index of a relationship that we know what to do with because it's on a common metric that's been rescaled, that's our standardized slope, which ranges from -1 to 1. So that's an R metric, or a Cohen's d, which will give you a d metric for standardized mean difference. So that strips off the units when we do that. But I still need to know, is my relationship sufficiently unexpected? If there really were no relationship, what % of the time would I find the one that I got, if there were none? To know that, I have to factor in sample size. And the way that I factor in sample size is the standard error. Estimate divided by standard error then gives you your test statistic. Once you have your test statistic, then you can figure out where you are back on the t-distribution. Are you in the middle? Are you in the 95% that would be sufficiently expected? Or are you out in the tails, out past the cut point that you decided already based on your sample size and your alpha level and picking 2 tails instead of 1? So if your t, for instance, if t worked out to be 1, at every sample size, 1 would be well within expected territory. You would find a relationship indicated by that t-value of 1 greater than 5% of the time. So a t of 1 is non-significant, is expected, means I don't have enough evidence to reject the null. I don't have enough evidence to say that I found something. Because what I found is either not big enough or too noisy to be believed. How do I make the same size relationship stronger? More people. So T gets bigger for the same effect size with bigger N. What if T were -1? Same thing. The relationship is in the opposite direction. As X goes up, Y goes down, but that value is still well within expected territory. What if T were -4? Well, so long as you have more than what, like 10 people or something, I don't have the T table memorized either, that's going to be in unexpected territory. You have you have a histogram behind you, Jen. That's awesome. I just noticed that. Thank you. Well done. Yes, extra credit for sure. But yeah, a T of -4 means a very strong, a very unexpected relationship. Now I want to say strong, but I can't really say that because a T is a function of both effect size and sample size. If I have a sample of 1 million people, the tiniest little effect could be declared wildly unexpected. If I have only 10 people, a humongous effect could still be unexpected because it's too noisy. So the things that you would want to report then, to make sure that your reader has all the same information that you do in terms of how you're deciding to interpret this stuff. You want to tell them ahead of time what your alpha level is and whether you're doing one-tailed or two-tailed. That's sort of assumed in most places, but it never hurts to be explicit. You would have to tell them what technique, what type of modeling framework you're using, and then within that, you'd want to report the slope estimate. You'd want to report some kind of effect size for it. There's lots to choose from, and that's something we'll continue talking about throughout the semester, throughout the rest of the spring, I guess. The standard error as well. If you know the slope estimate and standardized estimate, let me clarify that. If you know the slope unstandardized estimate and the standard error, then you know T. And if you know your sample size, you know what the p-value is that goes with your T. So in practice, people usually take a shortcut and give you the slope, the standard error, and the p-value. But just having a T doesn't tell you how strong your effect is because T is contaminated by sample size. All right. Question 4, that was, how are we doing? Good. Okay. Other questions or things that I can clear up for you? Oh, I know one thing we didn't talk about today yet. Power. That's another thing we got to worry about. What is power? Relatedly, what is type 2 error? Error spelled wrong. There we go. Try again. There we go. What is type 2 error? Well, type 1 error is false positive. Type 2 error is false negative. So a type 2 error means there is a relationship there in reality, but I missed it. I said it's not significant. Conventional levels of type 2 error that are accepted in the social sciences is 0.2. Power is 1 minus type 2 error, power of 0.8. So you want to be able to have 80% power to detect an effect when you design a study. So that means you have to either start with an effect size and then figure out how many people you need, or, what is much more realistic, figure out how many people you can get, logistically, how many people it's possible to test, how many people you can pay, how many testing assistants you have, all the logistical constraints on research using real people, and then figure out what the minimum detectable effect size is at 80% power for that sample size. And there is a handout that I gave you several weeks ago that has power tables. So anytime that you declare an effect non-significant, power is potentially an issue. And the best way to address that issue is to provide an estimate of effect size. Because if you say something is non-significant, it's either that you had an effect that was worth finding, but you don't have enough people to find it, or you don't have an effect worth finding, and that's why you didn't find it. So if I have a correlation, for instance, of 0.1, that means a unit increase in X is associated with only 1/10 of a standard deviation unit in Y. Tiny effect. If it's non-significant, I can say, well, an R of 0.1 isn't that big of an effect. That's why I didn't find it. If I had an R of 0.5 that was non-significant, I would have a different argument to make. Well, yeah, I really don't have enough people if an R of 0.5, which is a good-sized relationship, is not significant. So there's two ways you can screw things up. You can declare something to be significant that's not, or you can miss something you should have found. With only one sample and one sample of real people, you will never know if you screwed something up. That's the cold, hard truth. Okay. Questions, comments, thoughts? Carly says, this helped. Good. You can declare something significant and it's actually not there. That's type 1 error. That's alpha. Or you can declare something non-significant that you should have found. That's type 2 error. That's beta. That's the opposite of power. Power is your chance of finding something that is there. You want as high a chance of finding that, meaning as low a chance as not finding something that's not there. Wait, I think I just said that wrong. Anywho, our cat chewed the power table print. Oh, that's fun. Yeah, other questions, and then yeah, you can top 10 styles of Zoomers. That would be fine after we're done with questions.